You ever think about how much of life is basically like, well, a coin toss? I mean, will the traffic be terrible today?
Yeah.
Will my team actually win for once?
Yeah.
It's all kind of up in the air, right? And to get a handle on that up in the airness, well, that's what we're doing today. We're going deep, really deep into the world of probability.
I like it. A deep dive.
Yeah, and the cool thing is we've got some seriously fascinating material to work with here. Stuff that really digs into how we actually measure uncertainty, not just, cross our fingers and hope for the best.
Yeah, you've pulled together some resources that really lay out like the mathematical framework of probability.
Exactly. We're talking definitions, axioms, all the good stuff.
hmm
Experiments, sample spaces, events. By the time we're done here, you should have a much clearer, stronger sense of how probability works,
Yeah.
not just fuzzy intuition.
Definitely. And we'll even trace how people thought about it historically, like those early approaches to probability.
Right, like where did it all begin? Let's start there. What were some of the initial ways people tried to wrap their heads around probability?
Well, your material dives into what's called the classical theory.
Okay, classical theory. I'm intrigued. What's that all about?
Imagine, for example, you're rolling a die, a normal six-sided die.
Okay, got it.
Now you want to know, what's the probability of getting a 4?
Okay, yeah,
The classical theory says, well, there's one way to get a 4, right?
yeah.
And there are 6 total possible outcomes. 1, 2, 3, 4, 5, 6.
So 1 out of 6.
Exactly. So the probability of rolling a 4 is 1 divided by 6, assuming, of course, that each side of the die is equally likely to land face up.
Yeah, that makes sense. It's kind of intuitive, right? Like if everything's fair and square, those are the odds.
Yeah.
But I'm guessing there's got to be more to it than that.
No, there definitely is. The material also mentions a different perspective, the statistical approach.
Okay, statistical. How's it different?
Instead of assuming things are equally likely, you actually gather data. You observe what happens in the real world. So let's say you flip a coin 100 times.
100 flips.
And let's say it comes up heads 53 times. The statistical approach would estimate the probability of getting heads as 53 out of 100, based on the actual results.
Ah, so it's like taking past performance as a guide. Interesting. So you've got classical, kind of the theoretical ideal, and statistical, rooted in real-world observations. But I have a feeling both of these approaches have their limits. What are some of the issues they run into?
You're absolutely on the right track. Both of these have their weaknesses. For the classical approach, the big problem arises when you don't have this neat, finite set of equally likely outcomes.
Yeah, I can see that. The real world's often messier.
Exactly. What if you wanted to figure out the probability of, say, a light bulb burning out at a particular moment in time?
Ooh, that's tricky.
Right, there's a whole range of possibilities, not just a few discrete options. Plus, that whole equally likely thing in the classical definition turns out to be, well, a bit circular.
Circular. How so? It seems like a fair starting point.
Well, think about it. When we say outcomes are equally likely, what are we really saying? We're essentially saying they have the same probability of happening. So we're using probability to define probability. It's kind of like trying to define fair as having an equal probability of each outcome.
Ah, I see the trap. We're going in circles. So if these early approaches had those kinds of fundamental hiccups, how did things move forward? What's the more, robust way of thinking about probability?
That's where the axiomatic approach comes in, which is, as you've pointed out, our main focus today.
Axiomatic, that sounds kind of heavy duty.
Well, it was a game changer. It revolutionized the way we understand probability. And the key figure here is a brilliant Russian mathematician, A.N. Kolmogorov.
Okay, Kolmogorov.
In 1933, he published a book called Foundation of Probability, and it laid out this brand new, incredibly rigorous framework, really solidified the whole field.
So this axiomatic approach, it's all about building a really solid logical foundation, I'm guessing.
Exactly. Instead of relying on this potentially shaky ground of equally likely outcomes, it starts with a set of very basic rules that any valid system of probability has to follow. These rules are called axioms.
Okay, axioms. So it's like setting the ground rules before we start playing the game.
Exactly. But before we dive into those axioms, we got to make sure we're all speaking the same language. There's some key terms we need to be crystal clear about.
All right, let's lay that groundwork then. What are the building blocks of this axiomatic world?
First up, we've got the idea of a random experiment. This is any process or action where the outcome is uncertain, even if you repeat it under the exact same conditions.
Okay, so it's not like, 2 plus 2 equals 4.
Mhm.
There's got to be some element of
Just
randomness.
think about rolling a die again. Even if you roll it the same way each time, you can't predict with absolute certainty what number you'll get.
Yeah, that makes sense. So what are the criteria for something to be considered a random experiment? What makes it officially random?
There are two main conditions. First, there's got to be more than one possible outcome. If there's only one thing that can happen, there's no randomness at play. Second, you can't know in advance exactly which outcome's going to happen. If you could predict it perfectly every time, it wouldn't be random, it'd be deterministic. Like flipping a coin two possibilities can't know for sure which side will land up.
Makes perfect sense.
Hmm.
Random experiment. Check. What's next on the vocabulary list?
Next, we have the concept of an outcome. This is simply one of the possible results of a random experiment.
So with our die rolling example, the outcomes would be 1, 2, 3, 4, 5, or 6.
Precisely. Each of those numbers represents a possible outcome when you roll the die.
And I'm guessing all those possible outcomes together make up what's called the sample space.
You're absolutely right. The sample space, usually denoted by a capital S, is the set that contains all the possible outcomes of a specific random experiment. And each individual outcome within that sample space is often called a sample point.
All right, sample space, sample point. Got it. Now let's try to put this into practice. What would the sample space look like if we tossed 2 coins, say a 1 rupee and a 2 rupee coin? Just once.
Okay, so for this, we need to consider all the possible combinations for the 2 coins. Since we've got 2 coins, each with 2 possible outcomes, heads or tails, we have a total of 4 possibilities. Heads on both, HH, heads on the 1 rupee, tails on the 2 rupee, HT, tails on the 1 rupee, heads on the 2 rupee, TH, and tails on both, TT. So our sample space, S, would be the set HHHA,
Yeah, that makes sense. We've covered all the bases. Now, what if we up the ante a little and roll, say, a pair of dice, maybe a blue one and a red one, just to keep track? What would that sample space look like?
Now, in this case, each outcome is going to be represented as an ordered pair, like X, Y, where X is the number on the blue die and Y is the number on the red die.
Okay, ordered pair.
Since each die has 6 sides, we've got 6 possible outcomes for the blue die and 6 for the red die. So the total number of combinations, the total number of outcomes in our sample space is 6 times 6. That gives us 36 sample points.
Whoa, that's a lot more possibilities.
Right, and we could even list them all out if you're up for it. It'd be like 1, 1, 1, 2, and so on, all the way to 6, 5, 6, 6.
I'll take your word for it. Let's try a different kind of example. The material mentions a person who has 3 coins. A 1 rupee, we'll call that Q for simplicity,
Right.
a 2 rupee, that's H, and a 5 rupee, R. This person takes 2 coins out of their pocket, one after the other. What's the sample space for that action?
All right, so let's think about the order here. The person could pick a 1 rupee coin first, then a 2 rupee coin, so that's QH, or they could pick the 1 rupee, then the 5 rupee, which is QR, and so on. If they pick the 2 rupee first, they could then get the 1 rupee, that's HQ, or the 5 rupee, so HR. And of course, if they pick the 5 rupee first, they can then get the 2 rupee, RH, or the 1 rupee, RQ. So our sample space S in this scenario would be QH, QR, HQ, HR, RH, RQ.
Got it. Each of those pairs represents a distinct sequence of actions. The order definitely matters here. All right, here's another one. What about the number of accidents on a busy highway in a year? That's a random experiment, right? What's the sample space for that?
In this case, well, we could have 0 accidents, right?
Yeah.
Or 1, 2, 3, and so on. There's no set upper limit, not one that we can easily define anyway. So the sample space here would be the set of all non-negative integers. That's 0, 1, 2, and so on. This kind of shows that a sample space doesn't necessarily have to be finite. It can be infinite.
That's a good point. Sample space doesn't have to be limited. All right, let's make things a bit more interesting. Imagine this. We flip a coin. If it comes up heads, we then draw a ball from a bag that contains 3 blue balls, we'll call them B1, B2, and B3, and 4 white balls, W1, W2, W3, W4.
Okay, I'm following.
But if the coin lands tails, instead of drawing a ball, we roll a standard 6-sided die. So what would the sample space be for this whole experiment?
Okay, so we need to consider both branches of this experiment. If we get heads on the coin, H, then we could draw any of the 3 blue balls or any of the 4 white balls. So our outcomes would be HB1, HB2, HB3, HW1, HW2, HW3, and HW4.
Okay, I see.
But if we get tails on the coin, T, then we're rolling the die. So we could get T1, T2, T3, T4, T5, or T6. So if we combine all those possibilities together, our complete sample space S would be HB1, HB2, HB3, HW3, 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 HW4, T4, T1, T2, T3, T4, T5, T6.
That notation's really helpful. You can clearly see how the experiment could unfold step by step. Okay, one last sample space challenge. This one's also from the text. Imagine tossing a coin repeatedly, over and over, until we get heads for the first time. What would the sample space for that look like?
Okay, so think about it. We could get heads on the very first toss, right? That would just be H or. We could get tails and then heads, so TH. Or we could get tails, tails, heads, so TTH. And so on and so on. We could theoretically get a really long string of tails before that first heads pops up.
Yeah, potentially an infinite number of tails.
Right. So the sound space here would be HTH, TTH, TTTH, TTTH, and so on. Another example of an infinite sample space.
These examples really highlight how crucial it is to carefully define the sample space before we even start talking about probabilities. Actually, the material even points to exercise 16.1 in the textbook, specifically questions 1 through 7, which offer practice in describing sample spaces for different scenarios, like tossing a coin 3 times or rolling a die twice. It's like, step 1, figure out what all the possibilities are.
Exactly. Once we've got that sample space nailed down, we can move on to defining what we mean by an event.
Okay, events. What are those in the world of probability?
An event, which we usually represent with a capital letter, is essentially any subset of the sample space.
Okay, so a part of the whole set of possibilities.
Exactly. It's basically a collection of one or more outcomes from our random experiment.
So if we think about rolling a die, and our sample space is 1, 2, 3, 4, 5, 6, then the event, rolling an odd number, that would be the subset 1, 3, 5, right?
Spot on. And we would say that this event, let's call it E, has occurred if the outcome of our experiment happens to be one of the elements in that set E. So if we roll a 3, which is in E, we'd say, yep, event E happened. But if we roll a 2, which is not in E, then event E didn't occur.
That makes perfect sense. It's like defining a particular condition, and if the outcome meets that condition, the event has happened. Now, the material then goes on to talk about different types of events. It starts with what are called impossible and sure events.
Those are kind of the extremes, right?
Yeah, it sounds like it. So what makes an event impossible and what makes an event sure?
Well, the impossible event, that's represented by the empty set, denoted by the symbol C, this event contains no outcomes from the sample space. So basically, it can never happen. Like if you roll a standard 6-sided die, the event rolling a number greater than 6, that's impossible. There's no way to get a 7 or higher on a regular die.
Right. That's logically impossible. What about a sure event then? What would that look like?
The sure event is basically the entire sample space, S. Since the outcome of any random experiment has to be one of the elements in S, the event S is guaranteed to happen every single time we run the experiment. Going back to our die example, the event rolling a number less than or equal to 6, that's a sure thing. Every possible outcome meets that condition.
So impossible event can't happen, sure event always happens. Those are the two extremes. What other types of events do we need to be aware of?
Well, there's also the simple event, sometimes called an elementary event. And a simple event, this is an event that contains just one outcome from the sample space.
So if we go back to tossing 2 coins, and our sample space is H, 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 T, T, H, and T, T, then the event of getting heads on the first coin and tails on the second, that would be a simple event because it's just that one outcome, HT.
Exactly. And if we had a sample space with, say, 5 different outcomes, we'd have 5 simple events, each corresponding to one of those outcomes.
Makes sense. Yeah. So a simple event is like zooming in on a single possibility.
Precisely. And the material even mentions a little notational shortcut. For a simple event, instead of writing it as, say, PHT, we can just write it as PHT. A little less clunky.
Oh, that's handy. Now, if simple events are the single outcome events, I'm guessing there must be events that involve more than one outcome. What are those called?
Those are the compound events. A compound event is any event that contains more than one sample point. It's a combination of 2 or more of those basic outcomes.
So if we think about tossing 3 coins this time, and our sample space is all the possible combinations, the event getting exactly 2 heads, that would be a compound event, right?
Exactly, because it would include the outcomes, HHT, HTH, and THH, 3 possible ways to get exactly 2 heads.
Right. So compound events are like bundling multiple possibilities together. Now, the material starts talking about what it calls the algebra of events. What's that all about? It sounds a bit intimidating.
It might sound fancy, but it's really just about how we can combine events to create new events, kind of like we do with sets in math.
Okay, combining events. I'm listening. What are the different ways we can do that?
Well, one of the basic operations is finding the complement of an event. So for any event A, we have the complementary event denoted by A prime A, which basically means not A.
So it's like the opposite of event A.
Exactly. It includes all the outcomes in the sample space that are not an A. So if we think about rolling a die and event A is getting an even number, so 2, 4, 6, then the complement not A would be getting an odd number, so 1, 3, 5.
Makes sense. Everything that's not an A is a not A. What about combining two events, say A and B? What are the different ways we can do that?
One way is to look at the event A or B. This event occurs if either A happens or B happens or both A and B happen. It's represented by the union of the two sets A-B.
So it's like a more inclusive or, either one or the other, or both.
Exactly. Then we have the event A and B, which is a bit more restrictive. This event occurs only if both A and B happen at the same time. It's represented by the intersection of the two sets, A-B.
So both conditions have to be met simultaneously for A and B to occur.
You got it. And then there's also A but not B, which occurs if A happens but B doesn't. It's represented by the set difference A-B, which includes all the elements that are in A but not in B.
All right, so we can find the complement, the or, the and the but not. Seems like we've got a whole toolkit for manipulating events. Now, the text gives us an example to illustrate these operations. Let's say we roll a single die, and A is the event getting a prime number, so that's 2, 3, 5, and B is the event getting an odd number, which is 1, 3, 5. Can we walk through how to find A or B, A and B, A but not B, and not A, using those operations?
Absolutely. Let's break it down. Our sample space S, remember, is 1, 2, 3, 4, 5, 6.
Okay, got it.
So first, A or B, that's AAA, which is 2, 3, 5. If we combine all those elements, we get 1, 2, 3, 5.
So A or B is the event of rolling a 1, 2, 3, or 5.
Exactly. Now let's look at A and B, which is AB, that's 2, 3, 5, A1, 3, 5. The elements that are common to both sets are 3 and 5. So A and B is the event of rolling a 3 or a 5.
Okay, so both conditions have to be true now for A but not B. That's AB, which is 2, 3, 5, 1, 3, 5. If we take away the elements that are in B, we're left with just 2.
Right. A but not B means we roll a prime number that's not odd. And the only prime number that's not odd is 2.
Got it. And finally, not A. That's AA, which means all the elements in S that are not in A. So 1, 2, 3, 4, 5, 6, 2, 3, 5 leaves us with 1, 4, 6.
Exactly. Not A is the event of rolling a number that's not prime.
This example really clarifies how those set operations actually translate into meaningful events. Now, the material then delves into another important distinction: mutually exclusive and exhaustive events. What do those terms mean in the context of probability?
They're really important for understanding how we calculate probabilities. Two events, A and B, are considered mutually exclusive if they cannot occur at the same time. In terms of sets, that means their intersection is the empty set, A-B. There's no overlap between them.
Can you give me a clear example of mutually exclusive events?
Sure, let's say you're rolling a die again. If A is the event the number rolled is odd, and B is the event the number rolled is even, those events are mutually exclusive. You can't roll a number that's both odd and even at the same time.
Right, it's got to be one or the other. What about events that are not mutually exclusive? What are those like?
Those are simply events that can happen at the same time, so their intersection is not the empty set. Going back to our die, if A is the event the number rolled is odd, and B is the event the number rolled is less than 4, those events are not mutually exclusive, because you could roll a 1 or a 3, and that would satisfy both conditions.
So there's some overlap between those events. They're not completely separate. Now, the material makes a point of saying that simple events in a sample space are always mutually exclusive. Why is that?
Think about what a simple event is. It's just one specific outcome. So if you've got two different simple events, they must be representing two different outcomes in the sample space. And since you can't get two different outcomes on a single trial, those two simple events can't happen at the same time.
Ah, I see. They're like two separate points, no overlap possible. Okay, so we've got mutually exclusive events. What about exhaustive events? What makes a set of events exhaustive?
A set of events is exhaustive if, together, they cover all the possible outcomes in the sample space. In other words, at least one of those events has to happen every single time you run the experiment.
Can you give an example of exhaustive events?
Sure. Imagine we're rolling a die, and we define 3 events. A is getting a 1 or a 2, B is getting a 3 or a 4, and C is getting a 5 or a 6. Those 3 events together cover all the possibilities on the die. So no matter what number you roll, one of those events has definitely occurred.
They leave no possibility uncovered.
Got it. And then there's the combination of mutually exclusive and exhaustive events.
Yeah, that's a particularly powerful combination because it means you've got a set of events where one and only one of them must happen every time. They essentially divide the sample space into non-overlapping chunks.
Okay, I'm picturing like a pie chart with each slice representing a different event. Exactly. The text gives a couple of examples to illustrate this. One involves rolling two dice, and there are events defined based on the sum of the numbers. The question is to figure out which pairs of those events are mutually exclusive.
Right, so which ones can't happen at the same time?
Exactly. And then there's another example with tossing a coin 3 times. It shows how 3 specific events are not only mutually exclusive, meaning no two can happen together, but also exhaustive, meaning one of them is guaranteed to happen every time.
That makes sense. It's like creating a complete and non-overlapping partition of this sample space. And as you said, this kind of setup is super useful in probability calculations.
Absolutely. And the material even points us to exercise 16.2, questions 1 through 7, for more practice with these ideas. It really helps to solidify our understanding.
Okay, so we've covered a lot of ground here. We've defined random experiments, explored sample spaces, and even learned how to manipulate different types of events. It feels like we've built a really solid foundation. Are we ready to move on to the formal definition of probability itself within this axiomatic approach?
I think we're at a great place to do that. Now that we understand the playing field and the players, we can talk about the rules of the game, the axioms that tell us how to assign probabilities to events in a way that makes sense mathematically.
Okay, the axioms. Lay it on me. What are those fundamental rules?
Right. So in this axiomatic approach, probability, which is usually denoted by the letter P, it's defined as a function. This function takes an event, which is a subset of our sample space, and it assigns a number to that event. But not just any number. It's got to be a number between 0 and 1.
Okay, between 0 and 1, so like a percentage, kinda. 0% chance to 100% chance.
You got it. And this function, PE, has to obey 3 core rules, the axioms. The first one is called non-negativity. It simply says that the probability of any event, E, has to be greater than or equal to 0. Probabilities can't be negative. Makes sense, right?
Yeah, definitely. You can't have a negative chance of something happening.
Exactly. The second axiom is called normalization. This one states that the probability of the entire sample space, S, is equal to 1. Basically, this means that it's absolutely certain that something from the sample space is going to happen. One of those possible outcomes has got to occur.
Yeah, that's a sure thing. 100% certainty.
Now, the third axiom, this is the one that deals with combining probabilities. It's called additivity for mutually exclusive events.
Okay, additivity. What does that mean?
This one says that if you've got 2 events, E and F, and they're mutually exclusive, meaning they can't happen at the same time, then the probability of either one of them happening, so E or F, is equal to the sum of their individual probabilities. So PEF plus PF.
So if two things can't happen together, the chance of either one happening is just the sum of their individual chances. Makes sense to me.
And the material even points out a cool consequence of these axioms. You can actually deduce that the probability of the impossible event, which, remember, is the empty set, is 0.
Yeah, that makes sense logically. If it can't happen, the probability should be 0. But how do we get that from the axioms?
It follows from that third axiom, the additivity rule. Think about any event, E, and the impossible event. They've got to be mutually exclusive because they have no outcomes in common. Their intersection is the empty set. So according to that third axiom, the probability of their union, E or phi, is equal to the sum of their individual probabilities, PE equal PE plus P.
Okay, I'm following.
Now, the union of any set with the empty set is just the original set. So EFE is just E, which means PE plus P. And if we subtract PE from both sides of that equation, what do we get? PE plus 0.
Oh, there it is. The probability of the impossible event is indeed 0. Now, if we have a finite sample space, like, let's say, S has n distinct outcomes, what can we say about the probabilities of those individual outcomes based on these axioms?
We can say a few key things. First, the probability of each individual outcome has to be between 0 and 1. That's because each outcome is a simple event, and its probability has to obey those first 2 axioms.
It can't be negative and it can't be more than 1.
Exactly. Second, the sum of the probabilities of all those individual outcomes, that has to be equal to 1. This comes from applying that third axiom repeatedly because all the individual outcomes, they're mutually exclusive, and together they make up the entire sample space.
It's like saying one of those outcomes has got to happen, so their probabilities have to add up to 100%.
Precisely. And third, if we have any event A, which is a subset of our sample space, the probability of A is just the sum of the probabilities of all those individual outcomes that are in A.
So we can build up the probability of any event from the probabilities of the basic outcomes that it contains.
Exactly. And the material reminds us that we can simplify the notation for simple events. So instead of writing P, we can just write PO1 for the probability of the outcome PO.
Yeah, much cleaner. Then the text gives us a nice simple example with tossing a fair coin. It points out that if we assign a probability of 1/2 to heads and 1/2 to tails, that's perfectly valid because both probabilities are between 0 and 1, and they add up to 1. But it also shows that we could assign different probabilities, like 1/4 to heads and 3/4 to tails, and that would also be valid as long as the two probabilities are between 0 and 1 and add up to 1.
So the axioms don't tell us exactly what the probability should be, just that they have to follow those rules.
Exactly. The axioms set the boundaries, but within those boundaries, there can be different valid probability assignments. It then gives us another example, example 9, where there's a sample space with 6 outcomes, and we're given several different proposed assignments of probabilities to those outcomes. The task is to check if each assignment is valid based on the axioms. So some assignments are valid because all the probabilities are between 0 and 1 and they add up to 1, but other assignments violate the rules, like having a negative probability or having probabilities that add up to something other than 1. It's a really good way to check if a probability assignment is actually legit.
Absolutely. It helps to really internalize those axioms.
Now, the material then moves on to actually using these axioms to calculate probabilities of specific events. It starts with some examples. One of them talks about examining 3 pens in a row. Each pen could be either good, G, or bad, B. So we've got 8 possible outcomes.
Okay, I'm visualizing this. 3 pens, each one could be good or bad.
And we're assuming each outcome is equally likely. So the probability of each one is 1/8.
Right, because there are 8 total possibilities.
And then it defines an event A, exactly one defective pen. So we've got to figure out which outcomes satisfy that condition.
Let's see, that would be BGG, GBG, and GGB. Those are the only 3 possibilities where there's exactly one bad pen.
Exactly. And since each of those outcomes has a probability of 1/8 and they're mutually exclusive, the probability of A is just the sum of those probabilities. So PA equals 18 plus 18 plus 18 plus 18 plus 38.
Right, straightforward addition because they can't happen at the same time.
Then it defines another event B, at least 2 defective pens. So we need at least 2 bad pens in the sequence.
Okay, so that would be BBG, BGB, GBB, and also all 3 being bad, BBB.
Exactly. 4 outcomes that meet that condition. And again, they're mutually exclusive, so we just add up their probabilities. PD plus 18 plus 18 plus 18 plus 18 plus 18 plus 18, 48.
Which simplifies to 12.
Makes sense. So when we have equally liked outcomes, it's really just about counting how many outcomes satisfy the condition and dividing by the total number of outcomes. But the next example shows us that we can handle things even when the outcomes are not equally likely. It's about tossing a coin twice, but this time the probabilities for the 4 outcomes are different. PHH equals 14, PHT, VTH equals 27, and